Okay, we'll pick up where we left off last week, talking about delta G and delta S. Remember that delta S is the entropy of a system, and delta G is the spontaneity of the system. It's the energy that's stored in a chemical reaction. It's like a potential energy. When we drop a brick from above our heads, it has potential energy that's converted to kinetic energy as it falls. The same way as if I drop a brick off a roof, it's going to have more energy as it falls further distance. Same way I pull a rubber band back, stretch it to the limit. It's going to have a bunch of potential energy that's converted to kinetic. The second I let go, it snaps back. Well, the same thing is done with chemical reactions. We have a low point and a high point, and the potential energy is going to be snapping back as it does a reaction, and that's our spontaneity. So we learned our basic reaction is delta. Oh, I got a note. So no, our basic reaction is delta G equals delta H minus T delta S. So how do we calculate delta H? Delta H is products minus reactants. Say that's equal to, well, our products is just one barium carbonate. 1, 2, 1, 3. And minus our reactants, which is our barium oxide and our CO2. You add those up, you got to remember subtract a negative. It's the same as adding a positive. So what we get is not 2,000 something, but negative 271.5. Units are kilojoules in a mole. Same thing for delta S. Delta S is products minus reactants. We say, well, our products are 112. Our reactants are 72.1 and 213.8. So we're going to get a negative number as well. 213. So this is an enthalpically favored reaction, but not an entropically favored. Entropy says, no, this does not want to happen. But enthalpy says, oh yeah, it's fine. So calculating delta H, delta G is delta H minus T delta S. So we need temperature in Kelvin to turn joules per mole Kelvin into joules per mole. But we also have to turn joules per mole into kilojoules per mole. So 173.8, but we have to say times, in 1 kilojoule, there is 1,000 joules. So what we end up doing is, so that big effect of the T delta S is blunted by the fact that this is all in joules. So this whole thing comes out to a positive 51.79. When I add that to the negative 271, you have only some. When I add that to the negative 271, we have 219. So our delta G is negative 219. As we proceed, you might be able to see that, oh, if temperature increases, this will have a larger and larger effect until we get to a point where it is no longer spontaneous. But at this temperature, it is very much so spontaneous. So, okay. Now, maybe you've noticed, maybe you haven't noticed that on occasion, you see these little circles at the top of our letters. This is a knot. We use that for delta G naught, delta H naught, delta S naught. This is called the standard energy of something. The standard free energy, the standard enthalpy, the standard entropy. It is a artificial state we use when calculating this, so that it doesn't matter where I calculate it, it's always going to be the same. If I do this in Aspen, Colorado, or Tampa, Florida, like Dusseldorf, Germany, whatever, we're going to be all the same standard states. The standard state is, say, if it's an element, it's a pure element. If it's a liquid or a solid, it's a pure liquid, it's a pure solid. If it's a gas, it's held at 1 atmosphere. If it's a solution, it's at 1 molar. For this way, it makes it very convenient. We can calculate this the same no matter where we're at. Now, with the way we set delta H for a pure element, that was 0. Well, we can also set delta G for a pure element as 0, meaning that the spontaneity of forming a pure element from a pure element it's at equilibrium. It's not going to react. It's already at 0. One other note is that with delta G, we assume if delta G is standard, we assume it's at 25 degrees unless told otherwise. With that in mind, it is possible to calculate the delta G of formation of a compound, or the delta G of a reaction, using only the tabulated delta G values. So on all the tables, we will have a delta H, a delta G, and a delta S. If it's at 298 Kelvin, we can actually just cheat and use the delta G. But if it's not at 298, that's when you have to use the delta H and delta S, because delta G is temperature dependent. But if we measure it from a standard point of 25 degrees Celsius, 298 Kelvin, it doesn't matter because it's the same. So, quick math here. What is the delta G reaction for this? So, just looking real quick. The delta G from carbon to graphite, well, or from diamond to graphite, products minus reactants. Products minus reactants, you'd get, oh, it's actually really easy, negative 2.84. So the reason I show this, are diamonds forever? No. No, they're not. Diamonds are actually this non-spontaneously favored. They are going to degrade into graphite unless you put work into it. Superman can crush a graphite into diamond, but it takes a lot of energy to put it into there. But remember, delta G tells us nothing about the time scale, nothing about the speed of reaction. It will react until it gets to the low point, but it will take thousands of years. Diamonds are forever on a human standpoint. On an Earth standpoint, no, not very much. It takes certain conditions to make them entropically favored. But so this is where we'll stop. We'll stop after this clicker question. Clicker question says, determine the delta G for this reaction. 2A plus 1B2 goes to 2AB. So we have 2 products and 3 reactants, and they're going to subtract from each other to calculate our delta G. We have our delta G values. A is 0. The diatomic B is 100 each for B2, and there's 150 for each AB. So I'm called early because this is artificially done. We've already done this. I had to re-record. Goofs on my part. The correct answer is C. We have two ABs. Two ABs. That means 150 plus 150, so 300. Negative 300 minus the reactants, minus a sum of negative 100 and 2 times 0, which is negative 100. So minus negative 100. 300 plus 100 is negative 200, or answer C. That's where we're going to stop. Okay. Well, here's where we'll pick up where we left off. No, there we go. There we go. Okay. Well, that upper corner. Okay. There we go. Okay. Now, as I said, delta G is equal to delta H minus T delta S. So what this means is that spontaneity is not constant throughout an entire reaction. It is temperature dependent, because delta G, delta H is more or less constant at temperature. Delta S is more or less constant at temperature. But what that means is, so as this temperature changes, this entropy has a larger or smaller effect. So if I do this at 200 degrees, it's going to be different from at 300 degrees or 500 degrees or whatever that temperature is in Kelvin. It's going to make this entropy play a bigger effect. That was the problem we just did a few minutes ago with the barium oxide. Was we said the entropy times temperature was 51, and that lowered the spontaneity. Well, what happens if instead of 298 that was like 398? Well, 398 would have made the entropy effect of, instead of 50, almost 68. And if you keep going up in temperature, it's going to be bigger and bigger and bigger effect until finally you could say there is a point, conceivably, where this is no longer spontaneous. That barium carbonate would no longer form. So basically at high temperatures, when T is big, entropy has a greater influence. So we can think of 4 possible situations based on the signs of these. Now you can memorize this, you can have a chart, or you can just use your brain and just pickle your way through this. It's basically, remember that delta G is spontaneous when delta G is negative. The reaction is spontaneous when delta G is negative. It's non-spontaneous when it's positive, and it's at equilibrium when it's 0. So with that in mind, you can think about that. If delta H is negative, it's going to try to make this delta G negative. If delta S is positive, then a negative minus a positive is always going to be negative. So when delta H is negative, delta S is positive, this is going to be always spontaneous regardless of the temperature. Low temperature, it's going to work. High temperature, it's going to work. It's always going to work. When delta H is positive, so it's an endothermic reaction, and entropy is negative, so minus a negative is the same as adding a positive, it's always going to be non-spontaneous. There's not going to be a way to make this work by changing the temperature. So negative, positive, always spontaneous, positive, negative, never spontaneous. So the hard one is when they're either both negative or both positive. You have to really kind of think about that. If that's negative and that's negative, that means if this term, the T delta S, is larger than this term, the delta H, that means it's non-spontaneous. So at low temperatures, it's spontaneous. At high temperatures, it's non-spontaneous. So we have these, we can also look at these 4 charts, all the same thing. If they're positive, positive, it's going to be the opposite. So right here, this is the always spontaneous. This is negative, positive. No matter how the temperature changes, it's always below 0. This is the positive, negative. No matter how the temperature changes, it's always above 0. But here's the thing where it's like, oh, delta H is negative, but delta S is negative. So you can imagine time. So it starts spontaneous, and as it heats up, it suddenly no longer works. All right, positive, positive. It starts non-spontaneous, but as it heats up, suddenly it starts working because it drops down below H. And for these 2 situations, we can calculate the exact temperature at which this occurs, because we want to find that magical 0 point that is between spontaneous and non-spontaneous. So how would we calculate for that 0 point? Well, we set that delta G as 0 and solve for temperature. So we're going to add T delta S to the other side, and divide both sides by delta S. So you can get the temperature at which this is spontaneous is equal to delta H over delta S. So there's a way to find out at what exact temperature will a non-spontaneous thing become spontaneous. And now this should hopefully make sense. There is a real value when you take a negative divided by a negative, you get a positive number. When you take a positive divided by a positive, you get a positive number. But if you ever take a negative divided by a positive, you get a negative temperature. And because this is in Kelvin, what is the absolute lowest we can go? Anyone? Anyone remember what's the lowest temperature we can go in Kelvin?
0.
0. So can we have a negative temperature with Kelvin?
No.
No. So we're the ones that's always spontaneous. There is no inversion point. For the ones that are always non-spontaneous, there's no inversion point because we cannot get a negative temperature if absolute 0 is the lowest we can go. There's a reason why we use Kelvin and not Celsius. So we can actually calculate where that point is. Where does this cross if we know delta H and delta S? Now, will we use that very often? Probably not. But it is useful on occasion. Okay. Now, I'm going to just show this in practice. What is the delta G at 25? Now, and then, is there any temperature where that might change? So I'm going to unnote this. Now, just work directly on my slide. So delta H. Calculate our delta H. Delta H is our products minus our reactants. Now there's 2 ammonias, so 46.49 times 2 minus our reactants. Well, that's conveniently 0 and 0. So the delta H is just what, negative 46.49 times 2. So we have to count for all products and all reactants. So this reaction is written to work 3 hydrogens and 1 nitrogen form 2 ammonias.
Where did you get the 0 times 3? Okay, that's your react. That's okay. Okay, that's
Yeah, right there, right there. Sorry,
Nice, it's okay,
move that up so we can see it. Okay, delta S, same thing. Products 192.5 times 2. Oh, sorry. Oh, I need to erase that. Okay. Minus our reactants, which is 130.58 times 3 and 191.5. So, oh, I wonder if I can change the color. Red? Well, it'll be for the next time. So 192.5 times 2 minus 194.
It's negative 583.
Negative. I'm not sure about that.
I got negative 198.24 at the very end.
Okay, negative 583 is all the reactants.
Correct.
But you have to also, I was like at the very end, yeah.
The very end answer is negative 198.
Negative 198. That's what I was going for. Negative 198.24.
Correct.
Okay, so there's our delta H. There's our delta S. To calculate our delta G at 25, we're going to say delta G equals negative 92.98 minus 298 times negative 198.24 divided by 1,000. So, is this spontaneous first? That's the first question. 298 times 98. Yes, it is spontaneous. Not very spontaneous, but it is spontaneous. It will form some products. Is there a point where this is non-spontaneous? And that's what we're going to find. So the point where this is non-spontaneous is the point where delta G equals 0. So to find that temperature where delta G equals 0, we're going to say temperature equals delta H over our delta S. So we're going to say negative 92.98 divided by our negative 198.24. But then we're going to also remember that this had to be divided by 1,000 to turn them into the same units. Same units. So negative 92.98 divided by negative 0.19824 gives us a temperature of 469 Kelvin. 469 Kelvin. You can turn that into Celsius if you wish, but that is like 196 degrees Celsius. So if it heats up to twice the boiling point of water, suddenly this will not work at all. And this should hopefully fit with our understanding of this reaction. When we looked at this reaction based on Le Chatelier's principle, we said this is exothermic. We said in order to make this shift to form more products, we had to cool this down. We cool this down, we are removing a product, it shifts towards products. Well, in terms of this, if we cool this down, what are we doing? we are effectively lowering the effect of the T delta S. As we cool this down, if this goes from 298 to say 200, you're giving a more spontaneous reaction. We're allowing this effect to have a smaller effect on the spontaneity. So you get a more spontaneous reaction as this goes. So that's why I'm saying, like, this is building on what we should already know. That we say Le Chatelier is, well, it's going forward. It will go forward some, but if you cool it down, it would go forward even more. We said this guy doesn't, the K isn't very big. So we have to find ways to make this work. Well, the K isn't very big because delta G isn't very big. Is there ways to make delta G bigger? So the last clicker of this, once again, you don't have the clicker, you just send me an email, that's fine. At what temperature does this reaction become, so at what temperature does the reaction of the following thermodynamic property become spontaneous? At what point does delta G become negative? If I have delta H is negative 150, delta S is negative 500 joules per Kelvin, what temperature? Now, fortunately, they've already done the math for you. So it's either going to be always spontaneous or some relation of 300. You say 150 divided by 500, you're going to have some factor of 300. So they've done that math for you. The only thing you have to reason out here is whether it's above 300 or below 300. Now, there is a cheat way to do this. If you ever get to this point, you find our temperature is 300, and you wonder, is it going to be positive below or positive above? You use your delta G equals delta H minus T delta S. You try a temperature. If you try 300, you get 0. What if I try, what about 400? Do you get 0 then? Or do you get above? Do you get a positive number? Do you get a negative number? What about 200? Will that give you a positive number or a negative number? You can always try that. You say, well, that's below 300, so that must be that answer. Or that's above 300, so that must be that answer. So you can always try a temperature above or below to confirm your results. So you can reason this out, but you could always try a number and see, oh, plug something in. See, when does this become positive? When does this become negative? Give it till 3 minutes, so. Send your email away. Okay, that's 3 minutes. So, oh, last one in. Okay. So, to become spontaneous, to become negative, you have to have delta H being bigger than the T delta S. So, minus a negative means adding a positive. So, correct answer? Really? It is below 300. So if you take negative 150 minus 200 times negative 0.5, you get a negative number. So above 300, it becomes non-spontaneous. Above 300, it becomes a positive number.
So we take the 300, and then I'm confused on what we do next after that.
So literally, there is the 0 point is at 300. When you say delta G equals negative 150 minus 300 times negative 500 divided by 1,000. That's negative 0.5. If you multiply those two numbers together, you get negative 150 plus positive 150, which equals 0. So there's our 0 point.
Right, 300 is our 0 point.
Now we want to find when is delta G negative.
So this is when you were saying we could try answers.
You could try a number. You just say, well, what about negative 150 minus 200? I could go 299. I could go 299 and see what effect 299 would have. But this is going to have a much larger effect. That's going to be equal positive 100. Positive 100 times plus negative 150 equals negative 50. If I try negative 150 minus 400 times negative 0.5, we're going to get negative positive 200. So negative 150 plus positive 200 is going to be positive 50. So 400 is above 300. 200 is below 300. Which one of those results in a negative delta G?
The below 200.
The below 300. So that as I said, let it be a learning lesson, not the end of the world. But it's just like whoopsie doodle. Okay. Someone's getting a phone call. Okay, so there's like two other concepts we got to learn for this, and that's going to keep following us through to the next chapter. That is, what does it mean to be not at standard conditions? So delta G standard or delta G naught is defined as the free energy present when all compounds are at 1 molar or 1 atmosphere. So if we did this and did the Q expression for this, you would have a Q of 1. When all products over reactants are 1, the K or Q is equal to 1. But we rarely, if ever, do a reaction where we have 1 molar products and 1 molar reactants and 1 molar of everything. That's not how we do chemistry. We mix reactants together and then calculate what is the actual reaction going on. Our K expression is rarely equal to just 1. So this means delta G standard is a hypothetical more times than not. We're going to use the non-standard conditions because the products and reactants are rarely perfectly balanced. They're actually usually very out of balance. And so this suggests that a reaction will be more or less spontaneous until Q shifts to K. Until the reaction reaches equilibrium, the reaction will be very much so out of balance. So we can calculate the delta G non-standard by saying, here's the standard state conditions, and we're going to add a factor of R, T, ln Q. Q is just our reaction quotient from chapter 15. So it's coming back. So if I remember, our reaction is products over reactants, no solids, no liquids, and they're raised to the power of their coefficients. We've been doing this, the Q, the K, all that, all these last couple chapters. Make sure you still remember it. Now, R is units of joules per mole Kelvin. So you do have to convert that into kilojoules if you want to add that in. And the ln is just the natural log. But as I said, if all the products and reactions are done at 1 molar in 1 atmosphere, Q equals 1. The natural log of 1 is 0. And so if this is 0, all that drops out. So the basic statement is when everything is done at 1 molar in 1 atmosphere, delta G is equal to the delta G standard. So by definition, when everything is 1, we're at delta G standard. But when things are not all 1, we are at a different delta G, which could be larger or smaller depending if we have more reactants or less reactants. But remember, as a reaction progresses, Q will approach K. So as a reaction progresses, delta G will approach 0 to get us to equilibrium. But delta G standard will not change, ever. It is a set artificially defined point, the point where we have 1 molar of everything. So delta G can be calculated all the time, but delta G standard, non-standard, is what we're actually looking at 9 times out of 10. So I'm going to finish up with this slide. But this is the slide that really comes up in the last lab, the thermodynamics lab. This means that, so if a reaction approaches 0, the delta G approaches 0 when Q equals K, we get that delta G naught plus RT ln K is going to be 0. So we can calculate our K based on our delta G, or we can calculate our delta G based on our K, based on this reaction. The delta G standard is equal to RT ln K. So this is the only way we could calculate K at a different temperature other than physically measuring the concentrations. So most of the times we calculate K at, 25 degrees, because it's at standard state conditions. But if I can calculate delta G at any other temperature, then I can calculate K at any other temperature. So knowing delta G will give us K for any reaction at any given temperature. But we can also now finally directly quantify how will temperature affect the K. Because remember, delta G is temperature dependent. If delta G goes up with temperature and becomes more negative, then K is going to get bigger at higher temperatures. If delta G becomes less spontaneous at a high temperature, then K is going to get smaller at a higher temperature. So how could we solve for K? K is going to be equal to you just invert everything. You divide by negative RT, and you do the inverse natural log. But so the lab, I'm going to finish up with this little fact about the lab. The last lab, which you'll eventually get to, we're going to have to do this. We're going to have to do this. We're going to calculate ln K. Let's see. Okay, well, that's okay. We're going to calculate ln K. And we're going to plot, this on the y-axis, and we're going to plot 1 over temperature on the x-axis. And because we're basically setting this is equal to delta H minus T delta S. And I'm going to divide both sides by negative RT. Negative RT. And what that gives us is ln K is our left side. Negative delta H over R times 1 over t plus delta S over R, because the t over t cancels out. So what we have, this is our y-intercept. There's our slope. Here's our x. And here's our y. We're going to literally plot ln k, which we're going to measure by measuring the expected concentration, and at the temperature at which this is at equilibrium. From there, we can calculate what's our delta H values, what's our delta S values, and we can calculate where is our delta G values for that reaction. And you can try to find out what is our values of delta H and delta S for the solubility of potassium nitrate. You're trying to find out what is our delta H and delta S values for KNO3 solid splitting apart into aqueous K plus and NO3 minus. That's that last lab. So, but you have to find your lnk, you have to find your 1 over t, and then we're going to make a graph of that. That's that last lab. That's what we're going to end for today. So I will, don't forget, turn in your tests, and I will speak to you again on Wednesday. So this has been the Chemistry Cowboy. Once again, if you like what you see, please like, please subscribe. I'll be posting more videos to give you the education you need. And I've been asked to put this disclaimer to Bethel students. Remember that the log and the online learning guidelines remain in effect while interacting with any type of instructional materials / sessions. That, over and out.